Okay, so let's do an example. I've just chosen an example for the TM mode. We'll do other examples in class. We've got a 200 megahertz TM wave. It's got an angle of 25 degrees, and it's traveling from media 1 to media 2. I've given you the media properties down here. They're lossless media. There's no attenuation. I've given you the magnetic permeabilities and electric permittivities for each of the media. And I also am giving you what is the initial amplitude of the incident wave, 17 volts per meter. And we want to determine the magnitude of the transmitted and reflected waves. So since this is a TM mode, the first thing that we need to know is, well, we need to know what the angle of reflection is. And from Snell's law, the angle of reflection is just equal to the angle of incidence, and it was given in the problem statement that that's 25 degrees. Since we're in the TM mode, we need to check Brewster's angle, and so that is given by the calculation inverse sine of 1 divided by the square root of 1 plus epsilon r1 divided by epsilon r2. So we take that inverse sine, and so Brewster's angle is inverse sine of 1 over root 1 plus epsilon r1 is 12.5 and epsilon r2 is 4.2. So we take that, do the inverse sine, get out your handy dandy TI-89s, and you'll find out that Brewster's angle is 30.1 degrees. Since the angle of incidence is smaller than Brewster's angle, total transmission does not occur. So we're going to have to solve for the angle of we're going to have to solve for the magnitude of the reflection, the magnitude of the transmission, and the angle of transmission. So because you'll recall that if theta I was bigger than 30.1 degrees, we would have no reflected component for the TM mode. So we've got that. So we need to next calculate, well, we have our choice on what we calculate next, but I'm going to calculate the angle of transmission. I've got angle of incidence and angle of reflection. Let's do angle of transmission. To do that, I have to know what the betas are in the two media. So I'll use the definition of beta that we gave, I think, in like the third lecture. So reaching back in the memory banks there, it's omega times the square root of the electric permittivity of the material divided by the speed of light. This equation here will be really handy for all your calculations for TEM, TE, and TM mode calculations. So put that on your sheets. And so that gives us beta 1 is equal to, we had a frequency, 200 megahertz. So I have to convert 200, that's F, so 2 pi F is omega. So 2 pi times 200 e to the 6 is omega. Square root for material 1, it's 12.5. And it's okay to go ahead and use 3 times 10 to the 8th here for our speed of light. Gives us beta 1 is equal to 14.81. And remember, wave number has units of radians per meter. Beta 2, the wave number in media 2 is just going to be equal to 2 pi times 200 megahertz, so that's omega. We need to put the square root of epsilon 2 here, which is just 4.2. Notice that I'm using relative terms, right? This formula shows ER. Yeah, that should be ER, excuse me. Formula is for ER, not total. That's because we have a C down here. So don't put in 12.5 times 8.854 times 10 to the minus 12 for either of these calculations. Don't do it here either. So using just the relative electric permittivities, we get 8.58 radians per meter. Okay. So now I can determine the angle of transmission from media 1 to media 2. That's given for by Snell's law, beta 1 over beta 2 sine of theta I, the angle of incidence, and I've calculated beta 1, calculated beta 2. I was given the angle of incidence, so that's sine minus 1. Beta 1 was 14.81 radians per meter divided by 8.58 radians per meter. Sine of 25 degrees, make sure your calculator's in degree mode. We get an angle of transmission of 46.98 degrees. So to calculate the reflection and transmission coefficients, I need to know the intrinsic impedances of material 1 and material 2, or media 1 and media 2. Notice they're both non-magnetic materials, meaning they have a magnetic permeability of 1 here. So recall that N, or eta, the intrinsic impedance of a material, is equal to N0 times the square root of the relative magnetic permeability to the relative electric permittivity. So for us, N1 is going to be 120 pi times 1 over 12.5, and that's equal to 106.63 ohms. And eta 2 is equal to 120 pi, which is the intrinsic impedance of free space, times 1 over 4.2. I've got it written over here. And the result of that calculation is 183.95 ohms. So now we've got the angle of incidence, the angle of reflection, the angle of transmission. We know the wave number for media 1 and media 2, and we know the intrinsic impedance of material 1 and material 2. So now what we need to do is we need to calculate the reflection coefficient and the transmission coefficient for the TM mode. So the reflection coefficient for TM is going to be N2, which is 183.95. We then take that times the cosine of the angle of transmission, so 46.98 degrees. We subtract off that N1, which is 106.63 ohms, and we multiply that by the cosine of the angle of incidence, which in the problem statement is given as 25 degrees. And then the denominator is the same, but it's a plus instead of a minus. So 183.95 cosine of 46.98 plus 106.63 cosine of 25 degrees. Make sure your calculator's in degree mode for this calculation, and you will end up with a TM reflection coefficient of 0.1299. The the transmission coefficient for the TM mode is equal to 1 plus the reflection coefficient in the TM mode. We have to account for the difference in the angles, though, and we use the theta I and the theta T in that calculation. And to do that, we just multiply 1 plus reflection coefficient quantity. We multiply by cosine theta I ratioed to cosine theta T. So now we've taken care of the effects of the angle of incidence and the angle of transmission. So this is equal to 1 plus 0.1299. We multiply that by cosine angle of incidence was 25. The angle of transmission was 46.98. Again, I'm in degrees. That gives me a transmission coefficient of 1.501. The magnitude and angle of the initial amplitude of the reflected wave is therefore equal to the reflection coefficient for the TM mode times E0I, the initial incident wave magnitude, and that's 0.1299, and we were given this value is 17 volts per meter. So that's 2.21 volts per meter. And then the angle of magnitude and phase of the initial value of the transmitted wave is equal to tau Tm E0I, which is 1.501 times 17 volts per meter equals 25.52 volts per meter. So interesting conclusion there. Our incident wave magnitude 17 volts per meter. 2.21 volts per meter of that were reflected. The transmitted portion, though, 25.52, bigger than the incident wave. And so that is entirely possible and, in fact, plausible for transmission. And that's because of the change from the media types there. So that's an example of TM wave propagation in dissimilar media.